so I will begin. Okay, so now what I'm going to cover in the second lecture is I will be focusing on oral emissions and the relevance to analyze and to learn about the magnetosphere, ionosphere, thermosphere system and the coupling between those different regions. And then I will focus on future prospect. So open question, I've been dealing with the first one earlier. Others, and of course the list is not exhaustive. Then what causes the energy crisis at the giant planets? And I will come back on this one in a minute, what I mean by energy crisis. What drives the hemispheric differences observed at Saturn in the magnetosphere and Aurora ionospheric region? What is the source for that? Especially for Saturn, where the rotation axis and the dipole axis are together. I mean, are parallel. I mean, there's not much difference. So it was surprising to observe an hemispheric difference. And also, is the variable rotation rate observed in the Saturnian magnetosphere linked to atmospheric dynamics? Variation rotation rate at Jupiter within a millisecond is the same over years and years. At Saturn, we have observed 6 minutes, up to 6 minutes difference over a few years. So that's very surprising, especially again with the symmetry that is holding at Saturn and not at Jupiter, at least the intrinsic one, though we see that it seems that there is not a symmetry and something is going on as for the influence on affecting the rotation rate. I never mention it, I realize, I'm sorry. But the outer planet, they are fast rotator. I'm speaking about the rotation rate. I mean, Jupiter and Saturn, they rotate in about 10 hours. So one of the questions that I mentioned is the energy crisis. What is it? We know there is one at Earth. Well, there is also one at the outer planets. What is shown here is the exospheric temperature. Do you remember when I showed the temperature profile at the beginning? We had an increase in temperature in the thermosphere, heat, due to absorption of solar radiation, extreme ultraviolet and infrared. And ultimately, in the exosphere, we had almost a constant temperature. So here is the exospheric temperature as a function of the average distance from the Sun, so for Jupiter, Saturn, Uranus, and Neptune. What is shown in red is the observed value at low and mid-latitude. I insist, low and mid-latitude. We're not looking at high latitude here. And in blue, you have the model value if you assume solar input only. You have few hundreds of Kelvin of difference. So solar heating alone cannot explain the exospheric temperature which was observed. You may want to ask what's going on here at Uranus. So first they observe a high temperature at solstice and then it decreases at equinox. And so far I had this graph, and then I had to add geometry because this year they published that it seems to continue to decrease a bit. And so it seems that you not only need to take into account season, but also the complex orientation of the solar wind with the magnetosphere and the atmosphere. So a very complex system that we really don't understand. But at any rate, there is a clear discrepancy, and so we're missing an energy source. So beside the solar heating, what are the other energy sources which are available? Particle heating via collision and chemistry. But actually, that is not as significant as ionospheric Joule heating. We have particle, well, I will come back on the Joule heating in a minute, so I will describe it in more depth later on. But it's occurring through auroral electrical currents at high and ion drag heating at high latitude. Well, it's at high latitude. We will need then to transfer this high latitude energy, this energy deposited in the high latitude towards low and mid latitude. Is it easy? Well, on fast rotator, there are then due to the centrifugal forces, that's not trivial. And dissipation of upward propagating wave Well, that was estimated, and though it brings some energy, there's no way that it can explain this huge difference. Not every time we look at, and not globally. So we will be looking at this source more closely, because remember, for Jupiter and Saturn, the solar heating is minor compared with there is a huge amount of energy which is deposited in the high latitude region. So, but first of all, before to look into the whole magnetosphere, ionosphere, or ionosphere, thermosphere, magnetosphere system, let's look at the aurora, which are like a TV screen of this coupled region. So what is an aurora? Well, auroral emission, the photomanifestation of the interaction of energetic extra-atmospheric species with an atmosphere. Photomanifestation, photo taken in the large sense. For instance, X-rays, UVs, visible, infrared, even gamma rays. And then you need an extra-atmospheric plasma or energetic population. Why extra-atmospheric? I don't want to take into account photoelectrons. They are energetic particles. They can excite, but actually the source of their energy is solar radiation. Here, the source of the energy is outside the atmosphere, from the space environment, for the outer planet, that will be from the magnetosphere. Of course, the particle source, like for Uranus, it may be the atmosphere. It's escape, but then it's accelerated within the magnetosphere, and then they stream back onto the upper atmosphere. So you need a source of plasma. It can be also the moon. In the case of Jupiter, it will be Io. In the case of Saturn, it will be Enceladus. Then they are accelerated. Well, as Fran mentioned this morning, that's not a big deal. There are different ways of accelerating particles, plasma in the magnetosphere, field-aligned electric field, waves, and so forth. And so we end up with an extra-atmospheric energetic particles, which are going to, from the space environment, and stream bombard the upper atmosphere. And through collision, they will excite the atmospheric species. They can actually, through collision, excite themselves. And, but there will be a species, or there will be chemistry, and ultimately an ion will be excited. And then the excited species will relax in emitting photon, which is the auroral light. So analyzing auroral emission, we will learn about plasma processes. We can learn about the source of the energetic particles. We can learn about the composition of the neutral. Actually, the first time that H3+ was observed in the solar system, that was in the auroral region of Jupiter through the detection of infrared emission by H3+. So, as a result, Aurora is a unique and valuable remote sensing probe in the solar system. So H3+, as I just mentioned, that's thermal emission. So you have auroral emission, which can be in the UV direct excitation and then immediate emission of a photon. They can be also thermal emission, typically in the 3-4 micrometer range for H3+. And in that case, they are tracer of the ionosphere thermosphere response to magnetospheric processes, because the infrared emission is a function of the H3+ density and temperature. But they are not immediate. Typically, it's a 10-minute lifetime of H3+, so it means that it has time to undergo collision and get the temperature of the nearby thermosphere. And also, it's destroyed by hydrocarbons. You remember I mentioned that hydrocarbons are present below the homopause. So infrared emission through H3+ infrared emission will be a good probe for the ionosphere-thermosphere response above the homopause, but not below. And finally, H3+ is also key as a coolant same way as CO2 at Earth. You know, CO2 is a greenhouse gas, but actually when you are at in the mesosphere, when it emits infrared, the infrared escapes to space. So in that case, it's a coolant. And H3+ plays the same role, and it's a thermostat, efficient thermostat at Saturn, Jupiter, not as much as Saturn, but actually an efficient thermostat at Jupiter. At exoplanet, just on a side mention, if the exoplanet is too close, I mean, H3+, okay, exoplanet, but of the type of hot Jupiter or Jupiter-like hydrogen H2 atmosphere, dominated atmosphere. If the exoplanet is too close, then of the parent star, then you will have a lot of dissociation of H2, and then you will not be able to produce H3+, and then it will fail to cool. So you have to, so H3+ is a key coolant, especially at the exoplanet, but for too close, exoplanet too close to the star, then it just bursts in and can't regulate anymore as a temperature and escaping, I mean, have his atmosphere, as they call it, evaporate, but it's, I don't think it's a very good word, escaping to space. Okay, Aurora, so just some example at Earth, was primarily green light associated with the oxygen 5577 angstrom, and here is the Earth with the Aurora oval that Fran already mentioned this morning. You have example of Jupiter, also Fran mentioned it this morning, of the main oval, polar emission, also absence of emission or in this region or very weak, and also the footprints of Io, Ganymede, and Europa. You don't see the one of Callisto because it's expected to be most of the time. I think there was one observation because it's within the main oval. So what are those footprints? I mean, what are those emissions? They are located at the footprint, the magnetic footprint of the moon, as it's illustrated here with Ganymede. I mean, on those images, it's just a combination of a visible image of the planet with the ultraviolet observation from the Hubble Space Telescope added on it. At Uranus, and that will be the same at Saturn, at Neptune, you don't have a nice oval. Because remember, you have a very large angle between the rotation axis and the dipole axis. And as a result, you have more patches. But if you put them back into on a magnetic latitude map, then it will correspond to high latitude region. And also recently, there was, I will come back on this one actually later on. Oh, and just for the fun also, I mean, people were, yes, sorry. Well, there is semantic model, but actually it's used in the other way around. To have the location of the footprints, it helps to constrain the magnetic field line configuration. I mean, we have a rough idea of where you would expect it. If you need a process to generate those emissions. And with the moon, it's primarily, though there are arguments, due to Alphen wave. So you can argue can we call it Aurora or not, but that's beyond the point. But yes, they are actually, yes, using those way around. It's the anomaly, the magnetic anomaly that a friend mentioned this morning that was actually constrained with the location of the footprint of the moon, the magnetic footprint of the moon. Yeah, I mean, they have a magnetic model and it didn't fit, so they actually modify it and introduce an anomaly to be able to explain the location of the footprint all around. In some location it was fine, in some others it didn't really fit, and so they from that infer that there was an anomaly in the magnetic field. Okay, so let's look at, for instance, Saturn. So it has been observed the aurora in the UV. Like here you see it actually northern and southern at the same time. Here it's from HST, Hubble Space Telescope, here as well. And here, that's actually from the UV spectrometer on board Cassini. Here is from the infrared, from VINS in the infrared, infrared spectrometer on Cassini. And here is also from Cassini on the night side, in the visible. You can't see it on the day side. There's a reason from Earth you look at it in infrared or in the ultraviolet because of the scattering in the visible, the solar radiation scattering. But on the night side, you can actually see it. And I have another picture where actually you see it on the limb, so you can infer how deep it goes. And in the visible and also in ultraviolet, it derived it that it went well below the homopause. So, okay, I had a movie, but unfortunately, I can show it to you afterwards, but because it doesn't work on a nice meeting, I cannot show it to you, unfortunately. But it's very variable and in the infrared, very dynamic. Okay, it's nice to actually look at the location. For instance, the moon's footprint, we can constrain the magnetic field of the planet. But we can extract a lot more information by a spectroscopic analysis of those auroral emission. And that's done for Jupiter and Saturn, looking at the H2 Lyman alpha, H2 Lyman and Werner emission. And the same technique is used at Earth on the N2 LBH emission, so both in the UV. So what's happening is that at Earth O2 and at Jupiter and Saturn methane absorbed part of the spectral range emitted by those emissions. So those emissions are spread for about 100, 180 nanometer. And there is the part of this spectral window is absorbed by either O2 or methane, CH4. And the other part is not. So if you take the ratio between the brightness on the brightness ratio between the two spectral window, one where there is absorption by methane or oxygen and the other is not, then you will infer the column of methane at the region of emission of the auroral emission. And if you have the column, it means that you know where the emission occurred if you have a model telling you, so I'll explain it again. You have strong electron precipitation. This time you have to have the electron precipitation penetrating, in the case of Jupiter and Saturn, below the homopause. In that case, here's the homopause, and here's where the emission is occurring, where those energetic particles deposit the energy. You have emission of H2 Lyman and Werner. This emission, it will go in all directions, and in particular will escape, or try to escape. But part of it is going to be absorbed by methane between the where it was emitted to the homopause, and finally be able to escape. So if you take the brightness ratio between the spectral window which undergoes absorption by methane and the other which doesn't, you will derive the column of methane. And so if you have a model telling you what's the density, the profile and altitude of the methane, you will be able to say, the emission was at this altitude. And then if you have a model of energy deposition of the electron, then you know the more energetic the electron, the deeper in the atmosphere it will be depositing its energy, then you can infer the energy of the incident electron. And that's the principle. And then from the other window, from the spectral window which doesn't undergo absorption by methane, then you can derive the energy flux of the incident electron. Earlier I mentioned that the electron production rate is proportional to the energy flux of the incident electron, the excitation rate, and if it's like in the UV, the emission doesn't undergo any absorption, then the brightness in the window which associated with emission, which doesn't undergo methane, will be proportional to the energy flux of the particle. So the problem is, if the energy is too low, it will, of the incident electron, it will not reach the homopause. So there will be no absorption. So you can't use this technique. If it's too high, then you start to have absorption in both spectral windows, and then you can't infer the energy flux, and also the ratio will be biased. So on Earth, you can apply this technique from 0.2 to 20 keV, Jupiter and Saturn from 10 to 200 keV. And so at Earth, interestingly, you can use this technique to look at the discrete aurora. For Jupiter and Saturn, I can actually use it for both the diffuse and the discrete aurora emission. So similar technique are applied, but different limitation on the product. Okay. Come on. Sorry, it doesn't. Okay, so we have those auroral emission. We have their structure. We can infer information, quantitative information about the incident particle. And we can also infer information on the processes which induce those precipitation. So again, here's the main oval of Jupiter, footprints of Io, and polar emission, very active region. And then we can map them. Here is the polar view, here is the equatorial view, and here is the side view of Jupiter and its magnetosphere, and it's color-coded so you can compare those two polar view, the observation from Hubble Space Telescope and the schematic with the blue ring represents the breakdown of co-rotation between the planet and the magnetospheric plasma, where the auroral emission, the main oval, is associated, with the main oval being driven by, being associated with the rotation and the breakdown from co-rotation. And then you have this pink region, the Gaussian region, which is highly dynamic, which is associated with those active region here. And then the green region here, which is associated with the dark region, and maybe mapping to the far outer magnetosphere. Though the source of the magnetospheric processes associated with different regions, especially the polar region, are under still strong debate. Another way to infer information about magnetospheric processes and the coupling between the magnetosphere, ionosphere, and the thermosphere system is through infrared radiation. From the analysis of those emissions, you get not only information on the H3+ density and temperature, but also you can extract information on the velocity of the ion. Those observations I will describe in a minute are from the infrared telescope facility in Hawaii. So here is the velocity of the ion as a function of planetary radii. That's for Jupiter, and that's for Saturn. And here are the map of the ion flow or the different region on the polar view for Jupiter and for Saturn. So the main oval here, I mentioned already, it's associated with the breaking from co-rotation. And you see this oval also here. Okay, sorry. Here is this line, that's the brightness of the H3+. And this line here, it's associated with the velocity of the ion, with the dashed line represent exact co-rotation with the planet. Again here, that's the brightness of H3+. And here, the dashed line is pure co-rotation. And here, the solid line is the velocity So at the equatorial region, when you are looking well beyond the in the transparent, I mean the white region here, in the equatorial region, you have full co-rotation, as you see. Now, when you then there is a decrease, a depart from co-rotation, and that corresponds to the location of the main oval, which is associated with the breakdown from co-rotation between the magnetospheric plasma and the planet. And this breakdown, though it's not the driver of the main aurora, you can see it also in, at Saturn. And while the main auroral region are associated here for Saturn, you can see a peak here and a peak here, which is associated with the same process as the one which is driving the main oval, Jupiter. And also, I would like to mention this region here, which is a dim sub-rotation, and you can see that the velocity is it's almost stagnant in the inertial frame, but anti-rotating in the frame associated with Jupiter. As for what is driving it, there is too much controversy, and I will not discuss it further. But that's just a few examples of what we can use from the spectroscopic analysis of auroral emission to learn about the magnetosphere-ionosphere coupling. Another example, if I can manage to, yes, it's to compare the same auroral emission, but in different spectral region. So here we're looking at Jupiter, and this image has been taken by the Hubble Space Telescope at in the ultraviolet. It covers H2 Lyman alpha and Werner and H Lyman alpha. And this picture has been, it's combined data from the infrared telescope facility in Hawaii at 3.4 micrometer. And you can see that, for instance, the equatorial diffuse emission are about present in both cases and are quite in good agreement. The main oval, however, has quite some differences with strong emission here that you don't see in the infrared, and maybe due to strong hard electron precipitation. Remember, I mentioned that infrared is not sensitive. H3 plus is absorbed below the homopause. It's converted. It's not absorbed. It's converted. H3 plus react with hydrocarbons, and it's converted to hydrocarbon ions, and so you don't have H3 plus below the homopause. So if the energetic electrons are energetic enough to penetrate below the homopause and deposit most of the energy there, you are going to miss them in the infrared, while the UV can pick them up. Also, within the oval, like here, it's very dark in the UV, while it's not in the infrared. The infrared H3 plus emission are also sensitive to temperature, not only density, but temperature. And through Joule heating and the energy which is within the which is deposited in the main oval is then spread over the whole polar region and heat the whole polar region, and that is picked up by in the infrared, which is sensitive to the temperature of the atmosphere, and so to the response of the atmosphere, while the UV will be sensitive only to local particle precipitation. And finally, the ultimate comparative approach for auroral emission is to look at the response of planets and to a same event. So here, for instance, we had the Earth, Jupiter, and Saturn more or less aligned, and they were hit by, there was a CME which generated some interplanetary shock, which then first hit the Earth, and then Jupiter, and then Saturn. Here is, the Sun, Earth, Jupiter, and Saturn for quiet condition, And here is the CME and then the effect of the shock. So on a strong enhancement of the auroral emission on the night side, which then propagate towards the day side at Earth. At Jupiter, unfortunately, we didn't have emission. I mean, we didn't have HST looking at or any Galileo wasn't there anymore. However, Cassini was on its way to Saturn, and there was an increase in the radio emission, which correspond to. I mean, there are models which predict when the shock is expected at the planet, and more or less at that time there was the announcement which was seen by Cassini at Jupiter. And finally, the Hubble Space Telescope was looking at Saturn, and a few days later, a few weeks later, then the shock hit Saturn, and that was a dawn announcement, not a night side. So the way that the shock was perturbing the magnetosphere, and then ultimately the high latitude region is very different, with a night side announcement and propagating to the day side at Earth, while you have a dawn storm at Saturn. And another example, more recently, is when Earth, Jupiter, and Uranus were more or less aligned. And again, there were several shocks which were observed at Earth. Here is the hemispheric power which was recorded, and you have an announcement with events which are referred as A, B, and C. And then Jupiter, when the event A, means the shock which yield the event A, reach Jupiter later on, then you had announcement in the radio auroral emission. And finally, later on, that was in September, and then in November, with the Hubble Space Telescope, they observed some brightnesses in emission spot at Uranus. This example, it was for the event C, but they observed announcement for the three events. So it's really interesting to see how different the different planets react to the same. I mean, it's not exactly the same because the shock has evolved, but still the same solar event. So I think it's really important. The point of this lecture will be mainly the comparative approach is really key. Cross-body approach, but also a multispectral approach. Okay, so auroral emission, it's like a TV screen on the coupling, but let's look further on the thermosphere, ionosphere, magnetosphere coupling. So we have heard a lot about precipitation or bombardment of energetic particle towards the high latitude region, but the coupling goes much beyond that. There is exchange not only of particle, also the atmosphere provide a source of particle. For the magnetosphere, it's not perhaps dominant at Jupiter and Saturn, but it seems to be at Uranus, for instance. There is momentum exchange, and there is also energy exchange. So one example is the angular momentum exchange. So as Fran mentioned this morning, IO supply some neutral, which then are ionized. They are produced at the Kepler velocity and then picked up by the magnetic field. They are also moving outward, and through conservation of angular momentum, then their angular velocity should decrease. But what happens is that there is a current system which is established. You have an electric field because the particle have non-zero velocity perpendicular to this plane, so you have a motional electric field which is set up and which then generates equatorward electric field. So electric field associated, in the frame of the magnetospheric plasma, which then generates an equatorward electric field that's in the high latitude ionosphere. And that will also generate, increase the conductances and generate a current, a Pedersen current, so along the component of the electric field perpendicular to the magnetic field, and which will allow to close the general magnetospheric current system. What I said that the particle moving outward, they should lose angular velocity, but they extract then angular momentum from the atmosphere, which is propagated along the magnetic field line on the outward current, and allows them to co-rotate until the load on the ionosphere is too strong, and then it breaks the co-rotation. Fran mentioned it this morning that the magnetic fields are not anchored. I mean, the core of the planet generated those magnetic fields, but those magnetic fields are not anchored in the planet. And they more are the analogies that are like swimming on the ionosphere. I don't know exactly how deep they go, but definitely that's one possibility that they in a way follow the ionosphere, at least for part of this region. And the key thing is that while there is precipitation of particles along the magnetic field line, which then will generate ionization, increase the conductivities, at the same time you have closure of a Peterson current within the atmosphere, which help to close the current system, and there is a momentum which is extracted from the upper atmosphere to the magnetosphere. So through the current flowing within the ionosphere, you have Joule heating, which is represented here. Here's the mass density. That's the conductivity tensor, because you can have not only a latitudinal but also longitudinal component. So even though the Peterson conductivity is the dominant one, the whole conductivity needs also to be taken into account. Here is the electric field in the frame of reference of the neutral. So that's the electric field imposed by the magnetosphere, and the U here is the velocity difference between the ion and the neutral, yielding frictional heating. At any rate, the whole term is associated with collision between ion and neutral, but a slightly different processes, though it's embedded. I mean, it's combined. And that will then yield heating of the atmosphere. And this heating is largely dominating compared with the heating due to just the electron precipitation. You know, the electron precipitate, they excite, then if you have through exothermic, for instance, reaction, you can have energy shared and it could heat the atmosphere, but that is minor compared with the Joule heating through which is occurring through this current. But conductivity, well, we need to estimate them. So here's the Peterson conductivity, which is the estimate the mobility of the charge along the direction of the component of the electric field perpendicular to the magnetic field, and the whole, and that's associated with primarily ions. And lower down, it's speaking the whole conductivity, which is associated with the mobility of the charge in the direction perpendicular to the electric field and magnetic field, and it's associated primarily to electron. And then conductances are just the height integrated conductivity, height integrated conductivity, and I realized that I should move on. So here is the profile in pressure of the conductivity for Jupiter, and here for Saturn. And if you estimate the conductances for Jupiter, typical precipitation in the main oval are given by 60 keV and 10 milliwatt per square meter, and that generates 2 mho. And then for Saturn, it's 10 keV and 1 milliwatt per square meter. You have 12 mho. What's going on? So you have stronger precipitation at Jupiter, but actually the induced conductances, Peterson conductance, is less. And that is primarily, so What is shown here, this time we consider the same auroral forces, the same characteristic for the incident electron. And we then here's the values of the Pedersen conductances for Earth, Saturn, and Jupiter. The difference between Earth and Saturn, that's primarily composition. Ion composition is different, so the ion neutral collisional frequency will be different, for instance, and the ion mass will be different. And also the conductances, as I said, is a height integrated conductivity. You don't integrate over the, you integrate over a much smaller region, Earth compared with Saturn. The difference between Saturn and Jupiter is primarily the difference in magnetic field. If we go back here, the conductivities, there is a 1/b here. Also, B intervene in the zero frequency, but you have many this term 1/b. So with a much stronger magnetic field, that yield much smaller conductivity, and that's the main point. And I think that I should move on. Here's the, so I said that there is an energy crisis at the low and mid latitude. 0, at high latitude. We have all this energy deposited in the high latitude region. And here's the pressure as a function of temperature. And these black arrows represent temperature derived from observation, from infrared and UV observation. And the color lines represent simulation for different level of precipitation from 0.05 milliwatt per square meter to 0.5 milliwatt per square meter. Really not a very strong one. And there is a very good agreement. So auroral Joule heating is sufficient to heat the high latitude ionosphere. Now, if we dump all this energy, a lot more even in the high latitude region, can we then heat the low and mid latitude? Here's the temperature as a function of latitude, and the black points and symbols represent observations from different spacecraft and ground-based observations. And the blue and red line are simulation from a general circulation model for equinox and solstice. So again, in the high latitude region, we are doing a pretty good job. But at low latitude, we are far away from the observation. Remember, it's very hard to bring energy from high latitude to low latitude because we're a fast rotator. There are centrifugal forces. And what is illustrated here is the pressure as a function of latitude from the South Pole to the equator. And the green, the color, represent the thermospheric temperature, and the arrows represent the wind direction. And so there is, precipitation, and as I mentioned, after that yield to a heating over the whole polar region. But what happened is that there is the polar subcorotation because due to the equatorward electric field that yields westward ion velocity, so that generates a subcorotation, which drive a collapse ultimately of the high latitude region, and this collapse yield this current, and which cool the equatorward, the low latitude region. And the more you put energy here, the stronger actually is this return current. And as a result, then it cools the whole region here. Well, that was the static system. We impose an auroral forcing, which was constant over time. At Earth, if you impose a pulsating auroral input, then you have gravity wave which brings the energy towards low latitude. So perhaps that will be working. Here it's Hubble Space Telescope UV observations at Saturn. And you can see that it's quite dynamic over different days. So there have been some simulation using a global circulation model to see if a similar pulsation could work at Saturn. But so far, it has not been successful. The energy remains trapped in high latitude. And so, what next? Well, if we find a solution for the energy crisis or the hemispheric difference or the rotation rate, at any rate, it has to explain the whole rich data set that we have gathered at Saturn from the ground and of course, from Cassini. And so that's one key thing, and we will get even more observation as Cassini is expected to orbit until 2017. So the key thing is that if we could explain one type of observation, well, it has to also be able to explain the whole set in the infrared, visible, UV, altitude of deposition, characteristic of the particle. When we described the magnetosphere-ionosphere coupling, for instance, some models said, well, you know, we can perhaps explain the coupling if we assume a 0.1 mho, but you know, at Saturn you explain a value for conductance is significantly larger. So if you, to be able, I mean, the key thing is, whatever the solution, it has to be able to explain the whole set of observation. And also, will be coming soon in July 2016, Juno, which will be, thanks to a polar orbit, be flying just above or within the acceleration region and the high latitude region of Jupiter, and there is a lot of controversy as what are the processes associated with the polar region, so that should definitely help to hopefully settle the discussion. And so for the take-home message for this lecture, the auroral emission are a valuable probe of the ionosphere and ionosphere-thermosphere coupling in the infrared, and of auroral particle source, the ionosphere-thermosphere magnetosphere coupling, and the magnetic field line configuration. Because of time, I will skip through. And so the ionospheric conductances are large uncertainty, but definitely the values are expected to be significantly larger at Saturn than at Jupiter, even when the difference in electron precipitation characteristic is taken into account due to the difference is the magnetic field strength. Then simulation are key are complementary to the observation, simulation of the ionosphere-thermosphere system and the ionosphere-thermosphere magnetosphere system. Of course, if you do one ionosphere-thermosphere, you can be more, go into detail compared if you do the whole coupling, but those different type of models are key to be able to assess the upper atmosphere response to magnetospheric coupling. And as for the energy crisis, what next to investigate a shorter time scale as for the variability of the solar forcing. Electric field variability, the electric field is really not constrained and is strongly influenced the Joule heating. So that's also a large uncertainty. The role of wave don't seem to be able to explain at low and mid latitudes the energy crisis. They are not enough. However, what they could do is actually perturb the momentum balance and perhaps help to have this energy which is currently trapped at high latitude being transferred towards low latitude. And the lesson learned from Saturn hopefully will be very useful for the upcoming Juno and the Jupiter icy Explorer, which is so Juno is NASA and JUICE is ESA. This one is, so Juno will arrive in 2016. JUICE, well, if everything goes well, will leave Earth in 2022 and will arrive at Jupiter in 2030. And finally, of course, to extrapolate to exoplanet with different mission and mission one, but there is others also to dedicated to try to infer information in the atmosphere of the exoplanets. And the last one, I'm sorry, I'm running really out of time here. That's a promise, that's the last one, if I manage to show it, is that the key thing is comparative cross-body approach. It really challenges our understanding of the upper atmosphere, of the planet, of much beyond the just atmosphere, magnetosphere coupling, over all of our understanding of space physics. And comparative aeronomy is really key to challenge our understanding of atmospheric processes, of coupling with the neighboring region, and planet evolution, as well as open new doors for extrapolating beyond our solar system. And similar physics can be applied, but with very different settings. So it's really help comparative aeronomy to, or comparative body, whatever it's applied to magnetosphere aeronomy or other part of space physics, really understanding the physical processes, because ultimately it's the same processes which are occurring, but the relative importance is different. And it's really deepen our understanding of magnetospheric processes. So it's really an avenue that is, I think, very useful for students and researchers to apply. So thank you very much. And if you have questions, yes? Yeah? Okay. Yes. Yes. Yeah, that's correct. Yes. Yeah.
little bit of sense. All I can say is that obviously it must make a difference because when Mr. Carrington was looking at the sun the very first flare, what they saw was a slight change in the Earth's magnetic field because the flare was irradiating the ionosphere. That wasn't the magnetic storm yet. Right, so some changes that just happened have difficulty matching. Does it matter only to the ionosphere phenomena, or does it really structurally change even the geomagnetic field dynamics?
Yeah, go ahead.
I heard you worry about equatorial electrodynamics and fuel heating to the equatorial electrojets changing the vertical magnetic profile. Is there such a thing as equatorial electrodynamics at Jupiter and Saturn? Or can you show coupled into the fullest region?
Okay, so let me.
Yeah, go ahead. No, go ahead.
There's two ways. Let's say we'll be talking about radiation belts. They're very much like that. So in some ways, think about that. But that's a magnetosphere phenomenon. It's not an ionosphere phenomenon. And I'm not aware of any electrodynamics that are equivalent to these, what do you call it, that fountain
Fountain effect.
fountain effect.
Yeah.
Aware of anything like that. Of course, it's something that probably.
Because those are driven due to differences in connectivity between the EMF region and then along the terminator.
Yeah.
Yeah, that's a very interesting point.
I will check.
So I have a question
Yes.
about your difference in connectivity between Saturn.
Yes.
That's fine.
Yes. Yeah.
I know you went to the equation and explained it, but you know, I'm going to be a Cisco So, the strength of the magnetic field, you say, is the difference between that is an incredibly weak conductivity.
Yeah, but I had for Jupiter I had a weak energy flux. Okay, here I just it's not typical of Jupiter, but here because I wanted to compare under the same constraint, you know. So the reason I use.
No, I wasn't being critical. I was just being.
No, that's fine. Yes. Yeah.
Saying it's due to a weak field.
Yeah.
Why does it give me a field, or why if you take a system and you have an ionosphere, why does making the field very weak change the conductivity so much?
I mean, for Saturn, for instance, if the magnetic field is multiplied by a factor of 20, which then will make it about the same as Jupiter, then we find a decrease of 150 to 200 of the conductances. So that's really yes. Okay, it's mono.
Okay, but
Okay, physically. I'm sorry. Yes. Okay, so conductivity. So where does it come from? That's current. So you have, on the one hand, the conductivity times the electric field. On the other hand, the charge density times the velocity. And the velocity, you get it from the balance between the Lorentz force and the frictional heating between the ion and the neutral. So the Lorentz force is going to be changed strongly. So the velocity is going to be changed. So I would think that would come from that.
You just confirm that this is why I ignore
Part of the connectivity is how easy you can get charges from.
Yeah.
Direction, and worry about going from the size of it, influence collisions and all.
Yes, sure. And also, yeah.
It prevents electrons from moving the way they want to do.
Yes, okay. Sorry, I had more than mathematical. Sorry. Any other questions?